Hey guys, so today I'm going to be talking about these guys. You probably know them as LEDs. So, this is what an LED looks like most of the time. There is surface mount versions, but this is the standard 5mm, standard 3mm, and inside that you can see a 10mm. So to compare the 10 to the 5, or the 10 to the 3. Anyway, the way LEDs work is you put current across them and they light up. Simple enough. So, I'm sure you've all done this before, but you take a coin cell battery and you put the LED across it and it lights up. This is a rather bright white LED. Here is a kind of directional red LED, just used for indicators. You can see it can't really light anything up, unlike this white one. Pretty bright, huh? So, the way LEDs work is they're like a diode. Okay? Except a diode drops voltage. Not only do LEDs drop voltage, but they also emit light when they do this. So, if you really wanted, you could use this just to drop voltage. You could just cover it up, and, some people use it for that. Most LEDs are used as power indicators or as light sources of some kind. So essentially what LEDs do is they have a forward voltage drop, just the way a diode does. Usually it's 1.5 or 2, maybe 3. On some sort of Cree, XPG, star LEDs or whatever, they essentially have a like a hexagon shaped heatsink with the LED sort of in the middle here. And then the heatsink is there to dissipate the lots of heat it creates. And these can have up to like 4.5. So, but anyway, we're not going to use that. We're just going to take this standard white LED or, this pretty wimpy red indicator light. So the way they work is, and they have this forward voltage. So this is the voltage you want to put over the LED. Now, this is simple for an LED. Without the arrows, it's just a diode. But then, there's also, there's voltage and current, as Ohm's law tells us, which is current equals voltage over resistance. We always have to put a resistor here. So, for instance, if this LED's voltage drop is around 3.0 volts, this coin cell is around 3.0 volts. That means that if we were to get current, if we were to calculate our desired current, equals 3.0 divided by 0, well, it doesn't really work out. But essentially, if you're at the desired voltage, you do not need any resistor. Now, say you were to have 5 volts, which is common for a microcontroller, and you wanted to calculate the current. You wanted a current of, say, I don't know what this thing can take, but 20 milliamps is pretty standard. They come in 5, 10, 20. You can get XPG LEDs that go up to 750, but for the standard one, doesn't really matter. So if we wanted 20, which is 0.02, because that's really 1 amp, then 100 milliamps, 20 milliamps, and then 1 milliamp. So that would equal to 5. Oh no, actually. Okay, the series current is the same, but resistance, you want the voltage that the resistor needs to drop, not the voltage total, or the voltage the LED drops. So say your voltage was 5 volts supply, right? You don't want to do that. But if you had 5 volts supply voltage, right? So what we're doing is, if you have 5 volts there, what is this value, right? If you have 5 volts of supply voltage, and say your LED is one of these 2 volt varieties, right? That means that your resistor has to drop 3 volts. So you put 3 divided by X, which is going to be your resistance. Okay? So now, if we're to multiply by X, right, we get 0.02X equals to 3. Now, we could divide by 0.02 to get, on a calculator, which sucks, 3 divided by 0.02, it's going to be 150 ohms. So, most LEDs don't need that much resistance. I've seen LEDs that need resistance of like 5 ohms and stuff for higher currents. Now, in most cases, in a pinch, a 1K or a 330 ohm will do just fine. In case you're wondering, 330 is orange, orange, brown. So, because even if you were to drive a 20 milliamp LED at 1 milliamp, it would work absolutely fine. There would be no issues whatsoever, except it wouldn't be just quite as bright. But really, it's not a linear scale. It's logarithmic. So really, the extra current, it helps. And if you want to make a light or do some lighting or something, you definitely want that extra current. But if you're just going to use one as an indicator, like this one, to save current, you can, or to save power, you could just have 1 or 2 milliamps. So really, that's how you use an LED, and that's how you calculate the value of a resistor for an LED. So the formula is the LED currents would equal your resistance, which is going to be a variable. That's what you're solving for. And then your voltage would be the voltage minus the supply voltage minus LED forward voltage drop. Okay? So this would give you the voltage that your resistor needs to drop, and then you would solve for the value in ohms. Okay? So that's the formula. Now, here's an example. Right? We don't need any ohms to get this working right. And you can see that there's also another aspect of LEDs that makes them very desirable to use, is that unlike a light bulb, they switch on and off incredibly fast. So here, as you can see, there's no time at all for them to turn on and off. If I was to pulse an LED for 1 millisecond, it would stay on for 1 millisecond and 1 millisecond only. There's no warming up and slowing down time like there is on light bulbs. So I'm sure many of you have been to New York, and you've all seen those big screens. Those big screens are made out of LEDs that are being flashed on and off 10,000 times a second, okay? Obviously there's not white, there's red, green, and blue. But those LEDs are being flashed on and off 10 times, probably 5,000 times a second to give you the image, right? So you can use that. If you've seen those LED cubes, in fact, if I was to show you an LED being pulsed 1,000 times per second, it would go on and off, but in reality it would look constant to your eyes. So if you're wondering, how would I possibly use this, right? Well, say you wanted to dim an LED without changing this resistor, right? Like you were having a microcontroller and you didn't want to use one of those digital potentiometers, and you didn't want to, physically unplug the resistor or have a physical knob. Well, how could you dim this thing, right? Sorry. Watch. Anyways, I'm not sure if you heard that or not. I might just be talking to myself. But anyways, what you could do is you could still drive it at the regular voltage with the same resistor and stuff. But if you were to flash on and off, say, 2,000 times per second, right? But you were to keep the time that it was, if you wanted it to be bright, say up is when the time it's on and down is the time when it's off, you would do something like this, right? So that way it's on most of the time. Now if you wanted to dim it, you could make it off most of the time, like that, and that would make it much dimmer. So this is something called pulse width modulating, PWM. Pulse width modulation. This is a technique that can be used with LEDs due to their very fast switching on and off, time. You can also get, besides white and red, you can get variants of LEDs that have 2 LEDs in one, where they have 3 leads, a ground lead and 2 anodes, or opposite. You can get ones where if you were to put it on the battery one way, it would light up one color, and if you were to put it on the other way, it would light up another color. There's an LED in the backlight of this LCD, one in this flashlight. You can get LED matrices. I've talked about those. You can get infrared LEDs, like that one. All sorts of LEDs, very useful. Use them as indicators to light up something. Infrared LEDs, like in the laser keyboard, which isn't finished yet. Really, LEDs for almost anything. So But warning, if you were to put one on a 9-volt battery, say for example, it will fry, which is something that can be done for fun. So, anybody want to have some fun here? We'll just get some. We'll put the positive on the positive, negative on the negative, and I'll show you what happens when you put too much voltage onto an LED. This will happen with too much current as well. So just space those leads apart. Connect the positive. The positive. This also happens if you put it on backwards. So look at that. It's not even the right color. It just died. Smells pretty bad too. So, obviously you don't want to over put these things. Now if I was to put it on the coin cell again, would it light up? No. It doesn't. Throw it in the trash. So, do that by yourself. It's kind of a fun little experiment. So, that's everything you need to know about LEDs, pretty much. And if this resistor or whole resistor thing confuses you, just use a 330 ohm or a 1 kilo ohm resistor, and they won't be nearly as bright as this. And if you should really look in the datasheet for the LEDs what's forward voltage drop, because if the voltage you're using is the same as the forward voltage drop or less, don't use a resistor, or you can use a 0 ohm resistor, which is just a piece of wire. Theoretically, wire actually has resistance. But if it's over, then you really should calculate the current, the LED current, the current it's meant to handle. So you find that in the datasheet of the LED. Then you find the your VCC. Then you find the LED's forward voltage drop from the datasheet. You do VCC minus the forward voltage drop. Then you calculate for this variable here, R.